All right, so the first one is edit distance. And what pattern is this? Which one is it? Well, it is the one where we compare suffixes of different sequences. You could also compare the prefixes if you want, but if you can match the recurrence relation, that's really good. I also have these further questions before you code. What defines a state in this problem of edit distance? Let me bring this up. It has a fairly short description on the code. And so what would we use as our state? So think back to the previous presentation about recursion trees. What are we going to use to look at each state of the problem? Well, hopefully you saw that this recurrence relation, right, is really defined by these two things, I and j, right? So it's going to have two different dimensions, right? One is for the first sequence and one is for the second sequence, right? These indices, they define the suffixes. We start a suffix at I, we start a suffix at j, this is at apple, and maybe this is apply, right? So j might be all the way over here, but I is only at index 1. And what does each subproblem return? Well, the subproblem returns the same thing usually as what the problem asks. So it's the minimum operations for the current suffix denoted by I, j. And what are our base cases? So the suffix version of the problem, right? What happens when we take recursion and drill really far down? Well, eventually we get to some place like here, right? We might actually reach the end of one of the strings, okay? What should we do then? Think to edit distance. What happens when we reach the end of one of the words, but one of the other words isn't exhausted? Well, you can do either of two things. You can insert as many characters as there are left of the other word, or you can delete as many characters as there are left of the other word. I have written it concisely into one expression like this. And if we exhaust one of the words, we simply add the remaining length of the other word. So this collapses actually quite a few other base cases, but hopefully this makes sense to you, right? Because once you reach the end of one word, well, if you're not done with looking at this word, then you're going to add all the characters, right? Because that is the minimum amount of remaining operations now of turning an empty string into apple, right? All right, probably the crux of all the questions. Once you have these, how do these subproblems combine, right? And I'd like to stress that it's non-linear. A lot of times how you go about these problems. Sometimes you figure out how the subproblems combine and then you figure out what the base cases are. Right? So I'm about to show you the main body. So how did they combine? That's the crux of it. So insertion, right? So you insert a letter into word A, then that allows you to match the current letter at A, but then you match with B, so the index for the second word advances, right? And what about deletion? Well, you delete the current character of A, so you advance the index for A forward, right? This would be our example. Our first word is apple, the second word is apply. So let's say or maybe this is a better word. Maybe it's something like codes or something like that, right? Let's say you're here in the subproblem. Well, you could try deleting this, right? And then that's one operation. And then you see if this E might match with this P, right? It's also possible. In order to do that, it costs 1, right? To do that operation. And then there's replacement, where basically you're replacing A with something, or you're replacing maybe the D with something, you just replace it with P, right? In this case, you know automatically that there's a match, so you move both indices forward, right? And now you are at this state of the subproblem, or these two suffixes, right? There's one thing that isn't as part of this diagram. Let me show you. This is really important, and you probably have seen it already. If both the characters currently match, then you don't need any operation to change anything, right? So in this case, the subproblem is simply you advance both indices, right? Hopefully that makes sense, right? Because if you have A, P, P, L, E, and you have A, P, P, L, Y, there's no need to change prefixes that match, right? There's no need to do something like that. You just march all the way straight forward until they don't match. Then you do some of these operations, right? So this is basically G right here. You see us doing conditionals and then combining, right, a min operation on 3 different subproblems, right? The subproblems are insertion, deletion, and replacement. But if they match, then the subproblem is only just advancing both of these indices to try what happens at the suffixes. All right, hopefully that made sense. But I really encourage you to read Jeff Erickson's chapter 3 on dynamic programming as part of his wonderful book. All right, let's move on to this problem, minimum path sum. This one is actually very much like that robot coin problem. Instead of maximizing the amount of loot that a robot has over a grid, you actually, the robot goes to this n square right here, right? Because you start at the top left. Yep, top left, right? That's here. And then you go to the bottom right, which is our end. I wrote R because of I keep thinking about robots. This is which pattern? This note's pretty important, right? You can only move right or down. And hopefully immediately from that, you see that the pattern must be the explicit grids with limited direction pattern, right? Where each row and column depends on some number of other cells that have the answer already. Or maybe don't have the answer already, but you can perhaps recurse down and then compute their answers. So, but with explicit grids, I find it easier just to mutate the grid and write loops rather than writing recursion. But you could do it both ways if you want. But whatever's easier is what you should do. And the neighbors of this particular problem are simply the coordinate to the left and the above, right? Why is that? Well, if you look at right here, what is the minimum cost of arriving at 5? Right? The robot can only go right and down, so it must, to get to this 5, it must have come from this cell right here, or this cell right here, right? And if you know the optimal cost for, or you know the, well, optimal in this case is the minimum sum, right, of all numbers along this path. So the minimum sum here is 4, right? And the minimum sum here is what? It's 2, right? Because it had to come from up here, right? Because there's no number to the left. Okay, so let us talk about these very important questions. What data defines a state? That is, how's a subproblem defined? Well, a subproblem for an explicit grid is oftentimes just that cell coordinate. And what does each subproblem return? In this case, because we're just storing values in a grid, the subproblem is really the cell, right? So what does each cell contain? It contains the minimum sum to that particular grid cell, right? The minimum path sum. And what are the base cases? Arguably, there's one, but you might also make the argument that the entire top row is just a row of base cases, right? Because what you can do when you start this might spoil the next slide about like how we combine subproblems. But when you go over this grid, and because of the way that subproblems relate, right, it's very well formed. So basically all these cells, they depend on the cell to the left of them. So you can simply accumulate the base cases this way, right? And let's say we are at a cell like 1, 0, right? The first row down, right? And, oh wait, this is actually 1, 1. Yep. This is 1, 1. So when we get to here, well, we've already computed this cell from above, and we've computed this cell from the left side, right? So as you go in row order and just iterate this way, you should be able to compute the entire solution at the end cell, right? So that's the base cases, and I think I just described to you how to combine those subproblems. And it basically looks like this. And it's exactly what I said. So the grid, right, we depend on the row above the answer there. And we also care about the answer on the left of the cell. I did this weird thing in JavaScript where I did a ternary operator, and then if there was no left cell, well, I just said that this was infinity, right? And then I rely on the min operation to just keep this value, the value from the top only, all right? But other than that, hopefully this makes sense, right? This explicit grid one is hopefully pretty easy to see. There are much harder problems that follow this pattern, but I don't have examples of those today, but you'll be able to find them if you want to. All right, hopefully that makes sense. Wildcard matching. I think this one is a very good test to see on what we've talked about so far, essentially. So given an input string S and a pattern P, implement the wildcard pattern matching with support for question and star. It's very important to recognize that for this pattern, this is not regular expression matching. This is not a regex, meaning that A star does not mean that you match A some number of times, okay? This is you match A, and then you can match with the star, okay? So those are different, so just keep that in mind. They even have this example where you can simply match star, right? Because star matches any sequence of characters. There's a lot of things to keep in mind. If you have star but then P, right? If you want to match AA, the star could match both of these, but since there's no P and you need to match P, this would basically return false, right? If you have these two things as input for this problem, you should return false. And one thing to note, or a couple things to note, is that the matching should cover the entire input string. And this means that the pattern must be exhausted and the string must be exhausted, okay? You can't just match part of the string and the pattern is completely matched and call that true. That would be false, okay? Let's take a moment, think about which pattern this might be. This is a video, so I'm just going to tell you now. This is the same structure as at a distance. This is simply a variation on that problem with probably a bit more difficult to reason about base cases. At least for me, that's how it felt. I'm going to show you how I thought of this problem in terms of at a distance. But this is the pattern, right? I compare the suffixes of different sequences. I start off looking at my string at the first index. And I also start looking off my pattern, right? My star, wildcard A, right, at the first index as well, right? And I rely on the answers to the suffixes, right, the suffixes, in order to solve the problem. These subproblems overlap, right? You're going to see pairs of indices that are repeated as you do this type of recurrence relationship. So this problem naturally yields itself to this pattern. First of all, what data defines a state? Just like in at a distance, this is a pair of indices, right? And specifically, these define the suffixes starting at that index. So what does each subproblem return? Well, each subproblem should be like the larger problem, right? So each subproblem is actually going to be true or false. And what does that true or false mean? It means that that suffix starting at I can be matched with the rest of the pattern starting at J. So what are going to be our base cases? I think this one's actually tricky for this problem. Why is that? Well, for one, you got the star and you got the wildcard, right? The star matches any sequence of characters, including the empty sequence, right? When you do the wildcard, it matches any single character, so it has to be non-empty. So the star is probably more difficult. You actually have to match over nothingness as well. So let's see how we do that. Before that, what are going to be our base cases? To discover what the base cases are, what happens when we take the indexes all the way to the end? So I'm about to show you, okay? All right. So if you match the end of both the string and the pattern, that's true, right? We said it at the beginning when defining this problem to watch out. Like you have to have a full match for both the pattern and the string. So you return true in this case. But there's another edge case, and I believe I got one of these wrong when doing the problem, is that you might be at the end of the string, but not at the end of the pattern. But the remaining part of the pattern is just full of like asterisks, right? So if you got to here in the subproblem, maybe it's like APPLE, right? And you're right here. And the subproblem has you start at index 0. Well, that's okay, because if the rest of the pattern is star, then you get to return true. So I put this as one of my base cases here. And otherwise, right, if we got to the end of P otherwise, but there is some sort of S, there's some bits of S remaining, then I have to return false, right? Because I'm already over here. There's nothing else I can use to match, to keep matching the suffix that exists right now. So return false in this case. Okay? These base cases take some time to think about. Now let's get to the fun part, right? How do you combine these subproblems? All right, here's how I decided to combine them. You might find a different recurrence relation, and that's great. I actually like spelling things out pretty explicitly. I feel like this one is actually well reasoned. You could probably write this with fewer if statements and shorter code, but the time complexity for a lot of solutions I've seen is basically S times P, right? You could actually, so you might be worried about like this computation. You can actually cache this with a prefix sum. It's not a big deal. I didn't. It's true that I didn't, but you could. You could. So let's just go over how to combine these different subproblems, right? This is the recursion. And why are these the recursive cases? Well, let's take a look. Okay, so what happens when we have star? Okay, this is the more complex one. Well, you get to say that, hey, for our current suffix right now, this star, I don't know, this might be APPL, and then let's just have this E right here. You might decide that, hey, this star matches, and I'm ready to move on from this star, right? So initially, we are here, and now in salmon color, I'm going to say we moved over here, right? So that's this subproblem, right? And for S, we actually moved, right? We were here, and then we moved here, right? So this is the subproblem now that we look at, and we can see the result of that by calling a recursive call. Okay, great. But we're still in teal right now, right? And what we could also do, however, is with that star, is choose to not match. We choose just to not match this star. We could have our A remain here, right? The next subproblem is just simply going to look like this, right? We move on from the current character of the pattern. This star, maybe I just don't want it to match anything, right? That's a possibility. But I want to, so then if it's not matching anything, then I got to keep where I am at the current suffix of that string, right? So that's that subproblem in yellow. And then finally in green, what happens here is, well, I'm going to advance, actually. I'm going to move over here because I'm going to say this asterisk matched, but I don't need to move the asterisk, right? Because it has the potential to match any number of things, right? So it gets to sit pretty right here. Right, so these are our three different subproblems when you have a star, right, as your current character starting of that suffix. Okay, so those are the three subproblems, and there's no other ones when you have the current matching star right here. And finally, we get to the case where, hey, what if we just don't have a complicated case? We just have A matching A, right? Well, in that case, you just move both of the indices, right? Or you have the wild card and you can just match anything, right? Then you just get to move forward the indices, right? Boop and boop. And yeah, that's basically the problem. Hopefully this problem didn't feel too difficult, especially if you really studied edit distance, okay? This is a lot like writing depth first search, right? It just has different branching rules to it. Okay, so hopefully that recurrence relation makes sense. Next up, we're going to talk about Pascal's triangle. I might not want to spend too much time on this. Hopefully you see what kind of pattern it is, though, because I already alluded to it before. It is the one where you have limited direction. So why is that a limited direction? Because you only basically move down, right? Your subproblems only rely on things that are computed, right, as part of a directed acyclic kind of graph kind of deal. So specifically for Pascal's triangle, if you, hold on, let me just bring up that picture. So let's say this was index 0. Well, this is index 0. Oh, let's imagine these as rows, okay? So for the 0th row, this is index 0. For the 0th row, this one right here is index 0. And this is index 1. This is index 0. This is index 1. This is index 2. 0, 1, 2, 3. So you can see that basically this coordinate, right, depends on, well, 0, 1, 2, 3. The index at 2 depends on index 2 and index 1. So if you were going to use an array, you care about this cell and also this cell, right? So this would be the cell above and the cell left of the above. So diagonal left above, right? And that helps you compute this cell, right? So in terms of how we look at these problems, what defines a state? So our state is actually two indices, a row and a column, as we compute the individual cells, right? So what does each subproblem return? We actually, when we define this in terms of cells, the subproblem is simply the current value at that row of the Pascal's triangle, right? It is the sum of the above and the above left. So these are going to be numbers, okay? And the base cases are going to be basically, well, you start at row 0. You've got to have the initial value as 1. And then, I guess this is not part of the base case, but it's part of the computation that I set up. So these subproblems combined, we were just talked about this. It's the above and the above left cell. So what I do is basically I have a previous row and I have the current row that I'm going to work on. So for every row, yeah, basically I start a new array. And this new array, it's JavaScript, so every time I do an assignment on a cell that doesn't exist, JavaScript will extend that array up to that cell. This would obviously throw an error in Python. But basically this is the above cell, and this is the above cell and to the left. So all I'm doing is basically I have the previous row, right? And I start to build the answer. You know, it always starts at this 1, but then we build it up and we build it up all the way until we get to here. right? And then what happens is that I actually do a swap. So this becomes the answer because the answer is the row that I need. I'm actually just going to point this to previous, right? And then this gets garbage collected. And then I start the answer all over again, right? So make sure you guard, you have the proper bounds, right? Because the last value of that row is going to be 1. So you have to start this for loop at 1, right? Because you start looking at here and here, right? This is why we want to start the index at 1. So it's just very regular, very uniform. We don't have to check for if this is less than 0. Okay, all right. Hopefully that made sense. Again, this was not too difficult to see, hopefully. This problem has a pretty explicit recurrence relation where you don't have to do as much reading to kind of figure what that might be. All right, so let's move on to the next problem. Filling bookcase shelves. This one's interesting. And this, in my opinion, is actually a hard problem. So I'll give you a moment to read through this problem, or you can just skip my description because I'm about to tell you what it is. So you have a bookshelf basically, and it has a fixed width, right? And you just want to line up your books, and basically your books are going to be a certain tallness and a certain thickness, and for this problem you are not allowed to rotate your books, okay? None of that. No rotating your books, okay? They have to be as is, as given by the array. And your job is to figure out, hey, what is the minimum height of this possible bookcase, okay? So some of the books get to fit on the whatever shelf, right? But then the book, you also can choose to, hey, maybe put the current book on the next shelf. And depending on how you basically group these books on shelves, whether they're, by themselves or with certain other neighbors, you can acquire different heights for your bookshelves. Note that the shelf height itself, that's not factored in. You only care about the books, okay? If only the heights of the books mattered, basically. And you want to return the minimum possible height of that total bookshelf. Okay, and you have to do them in order, right? That means that you're not allowed to put book 1 after book 2, okay? That's not allowed. Book 2 has to come after book 1, but it can appear on the same shelf as book 1, or it can appear on the next shelf as in the minimum solution, okay? So you're not allowed to mess with the order of the shelves, the books, but you're allowed to decide which bookshelves which bookshelf a certain book belongs to. Okay, so which pattern is this? Which recurrence relation fits this problem the best? Well, hopefully you saw the one where it's basically we compute over contiguous partitionings, right? For this problem, basically we're doing something where we're looking through an array of numbers, right? And, at this current bookshelf, let's say, once we start a subproblem, we're deciding, hey, this book can start on this new bookshelf, and we decide that, hey, maybe this next book can be part of this bookshelf. And so if this next book is part or not part of this bookshelf, then, hey, isn't there some sort of natural partitioning that a subproblem could just figure out for us, right? Because if you had the minimum sized bookshelf starting from a suffix of the books, right? Then you could use your current height here, right? Our current height here, and you just add, right? Whatever's returned from the subproblem. And that is why this pattern fits. I like this one because the bookcase is the bookshelf is a literal partition, right? So you've grouped 2 and 3 into a partition, and then there's right? 4, 5, and 6, they can't belong to 2 and 3. And you're also dealing with contiguous things, right? So each book either belongs or doesn't belong to the current shelf. So you could also pick a different recurrence relation. And which one would that be? We've also seen it before. This is the pick or no pick, right? And you could write that other recurrence relation. I'll leave it up to you to look at other solutions. So the state, if you were to use the pick or no pick, you'd have to factor in the remaining shelf width as part of the recursive call, okay? I'm not going to do that. I'm actually just going to use this index as the state, okay? So what does each subprom return? It's the minimum height from putting book sub I on a new shelf. And what are the base cases? So what happens if you take the recursion down really far, right? Well, you'd be out of books, right? In that case is when you're at the length of books, right? So you return 0 because what is the minimum height when you have no books left? 0, because there's no books to put it on a shelf. All right, how do these subproms combine? And the hint is that it's going to look a lot like this, right? All right, this is one way of writing this. Hopefully you can tell immediately that, hey, we have one dimension and we have this while loop that goes through books. This immediately looks like n squared time because we're caching results, remember? All right, so what happens here? Well, we started a new shelf, right? This is what it means to start the subproblem at book index I. So immediately we should know that what height we have, right? So I'm going to look at the current book and I'm just going to extract its height. And I'm going to have to keep track of the remaining shelf width as part of my loop structure. And I want to start looking at the next book, whether we should or should not keep it within the current partition. So remember, book sub I, book index, represents the best partitioning to put for the suffix starting at book sub I. So here's the choice of putting the book on the next shelf, right? You just DFS starting this new book at the new shelf, okay? And once you have the answer to having that new book at that next shelf, well, you already have a height, remember? Remember we advanced the book index by 1 before starting the for loop. So we already have a book on our current shelf, right? So then we add our current height to, you know, the current book on next shelf, and we minimize that over all the other ones that we have or will see, okay? So that's going to be our min height for this subprom, our running min height, okay? If it happens that the book width, that there's not enough remaining width on the shelf, we break, okay? The book width actually is right here. I guess I could have put this if statement up here. That might have made more sense, actually. But nevertheless, I think that our base case actually handles that, or something like that. So next iteration, right? Now you got to prepare for next iteration, because what it means now, when we get to the next iteration, is that this particular book index, right? It used to be that we were picking this as partly to start a new partition, right? But now it means something. But now we already did the optimization over that subprom, right? Now we're over here and we're saying, hey, book index is actually going to be part of this partition now, okay? And this prepares us for looking at book index plus 1, right? Of starting this other subproblem next time, right? This would be the new bookshelf, right? The minimum height for the next bookshelf. And we need to combine that with the height of our current bookshelf. Okay, so that's why we update the height and we update the remaining width and we update the book index. Okay, I could have probably done something cleaner to move these up as like base cases up top, but I guess that's just how I decided to do that. when I did this problem last time. All right, so hopefully that makes sense. Hopefully you saw this recurrence relation, but if not, there's also another recurrence relation, right? It's that pick or no pick pattern, okay? So let's move on. This is palindrome partitioning 2. All right, so given a string S, you want to partition S such that every substring of the partition is a palindrome, and you want to return the minimum cuts needed for a palindrome of S. Okay, this is S, and well, you have a palindrome here, right? A is itself is a palindrome, right? And then you have another cut because A is also a palindrome. And then you finally have B, and it's like, hey, this is a palindrome. So the amount of cuts needed is maybe 0 for here, right? So I'm about to show you now. Hopefully you understand this problem. What kind of pattern should we pick here? Well, I like to see this as very similar to filling bookshelves. We have an accumulator, and then based off of something that happens, we try and increase our existing partition as part of our subproblem, while then being able to optimize over a future partition and combine it with our current subproblem, right? Somehow using our G right there, into finding the minimum cuts, right? Right. So this would actually be a min operation, right? Min over the amount of cuts that we already have for the current partition, and the minimum amount of cuts for over here. For this problem, let's talk about these questions again. What defines a state? Well, for this formulation, and this is not the only recurrence relation that you could use, I want to stress that I'm only showing you one way to do this. What defines a state is a single index, right? It's the suffix of that particular string. What does each subproblem return? Well, it returns the same thing as the entire problem, and that is the minimum cuts for a suffix string starting at index I. Okay, next up, what are our base cases? So what happens when you take recursion all the way down? You're gonna have something like, I guess, empty string, in which case you don't need any cuts, right? Another base case might possibly just be that, hey, I know that if I just check here to here, right, if the entire rest of the substring is a palindrome, right, it's the same forwards and backwards, then it's also 0. So there's multiple different types of base cases depending on what kind of recurrence relation you're really going to use. Which one did I pick? Oh, I picked this one. So I guess that's what this one looks like. Right? This is in Python. You just take the suffix of the string, and then you take the suffix of the string, but then you reverse it. If these are the same, you return 0. So just a little asterisk note right here. This is not cached. But if you want to do palindrome checks more efficiently, you'd probably want to do a pre-compute over a table, and for every I, j pair, and that is going to take O of n squared time. And what you can do is actually you can create an isPalindrome function that's that has its own caching. But don't worry about that. So how did these subproblems combine, right? That's kind of the main difficulty of this problem, at least. So what is this G right here, and how are we going to accumulate things? Okay, I'm about to show you, okay? It's this way, okay? So this is my base case. I just check, hey, if I have a palindrome here, and if I do, I don't need to cut it at all, right? It's already a palindrome, I get to return 0. I create a dummy value right here, and then I loop through from starting right now until later, right? So I might have this thing like ABA, right, that I start here at I. Who knows what came before it? Doesn't really matter, because I only care about what happens at I and suffixed afterwards. So if the current piece of the substring, right, if I start at I mean, if I start at start here, right, and I go to I, right, sorry, if I go to I, I want to start at this index where we have B. If this is a palindrome, then I get to recurse down, right? If it's not a palindrome, I don't get to do that. And why is that? Well, it's part of the problem, right? You have to cut a string, right? Right, into different palindromes, right? So here is one cut, but like ST is not a palindrome, so you're not allowed to do that cut. In fact, the only thing you're allowed to do is maybe cut right here, right? And then you start the subprompt here, and then, you know, you're going to scan through and you're going to realize, hey, this was the only subproblem that this was the only palindrome that I found starting at this particular index, right? So you're not allowed to like go and recurse down when you have AB. That's not a palindrome, okay? But you still want to continue the loop, right? You don't want to break out of it because you might find a palindrome later, right? I is going to increment and you're going to be like, hey, this is a palindrome. Wonderful. So now I'm going to start a new partitioning over here at I plus 1, okay? So that's basically how you optimize over that, right? You take the min count, right? The min count for the optimization over here is really simple. It's just always going to be 1, right? Because once you find a palindrome, that is 1 cut, okay? And then you go into the subproblem where you trust that you're going to get returned what are the minimum cuts for here, right? The answer might be 2, answer might be 3 or 4, right? But it's also possible that the answer is maybe, no, it's 1 or something like that. Anyway, there's other base cases. I think I wrote an even more efficient one today. I guess I did that caching for is palindrome here, so it would be faster. Yeah, so if you can actually have this as a base case if you wanted to, the amount of cuts that are needed if you reach all the way to the end, you can return -1. I do that because I know I'm adding 1 at each time. So if your entire recurrence relation was just if your entire string was a palindrome, right? If your entire suffix was a palindrome, basically this palindrome would see that and be like, hey, I'm going to add 1, and now you're looking at empty string, right? So this is going to be -1 that's returned here, and then this plus 1 cancels this -1 out, and min count is then 0, okay? So this is pretty dramatic if you want to look at, or I guess this is a very slow solution, not very fast, but just caching over the is palindrome check shaves you down about over a second. So, yep. That's that recurrence relation. I'm going to decide not to go over integer break. This might be a fun one for you to try. But the slides are here. The slides are here. They're up on Google Drive if you're ever interested in looking at the slides. Minimum cost to cut a stick. Alright, so in this problem, you are given a wooden stick of length n units. And the stick is labeled from 0 to n, and for example, a stick of length 6 is labeled as follows. And so basically you're given, this is extremely badly worded, but basically you have an array of cuts that you can reorder however you wish. And basically you can take the cuts in any order that you want to. And the cost of one of the cuts, okay, so there's going to be a cost associated with each cut you take. And depending on when you take it, it's different. And basically you want to minimize the total cost of all the cuts. And you have to take all the cuts, all right? So the cost of a cut is the length of the stick that's being cut, okay? And the total cost is the sum of all the costs of the cuts. So when you cut a stick, right, so I have this example right here. Let's say you take that cut at 3, boom, the cost is 6, right? But when you take this cost at 5, this cost is like 1, 2, 3, 4. So this is a plus 4 cost, okay? So on and so forth. So how might you think about a pattern that we've seen in order to solve this problem? Well, first of all, since you can rearrange the cuts however you want, you should think about maybe sorting them in some kind of order. Ascending order just works, so I just have cuts.sort. Anyway, this pattern now, let us have the reveal. It is the divide and conquer, the linear cut point one. And that is basically the same type of problem as matrix chain multiplication. I actually feel like the editorial for this problem is actually very well written. The code is very clean. So if you don't like my solution to it, yeah, just go look at the editorial. I'll show you mine. So when taking this type of pattern, what type of state are we looking at? Oh yeah, first we sort the cuts, and then we define our state as basically I, j in the cuts array. And this defines to us the bounds for what cuts we can take, okay? So these are bounds over the cuts, which is an input array. Okay, and the subproblem, each subproblem has to return just like the main problem, right? And that is going to be the min cost for a particular I, j, what I actually write. The minimum total cost of cuts done in some order in the interval. Well, it's done, yeah, you do the cuts in some kind of order, but that the interval itself is ordered from I plus 1 to j minus 1, or I to j if you do it that way. Depends on what specifically recurrence relation is. I find that the recurrence relation used by the editorial is much cleaner than what I'm going to show you. What are the base cases? So most of the ways to solve this problem revolve around reducing the problem size until nothing can be cut. The editorial, that is going to be if the left and right, the left and right, I or j, I minus j equals 1, right? You can't cut if you have this single block, right, between, let's say, 1 and 2, right? You can't cut that any further with a problem. So how do we combine these subproblems? And this is basically going to look like that exact same structure, where we do something in the middle. Well, basically for this recurrence relation, right? Basically we have some midpoint, and we're going to try all candidates for the midpoint, and we're basically going to recurse down, right? On the left side and on the right side, right? And we have some way to combine these subproblems, and it's most likely going to be a min operation because we're minimizing a cost, right? So this current mid is going to give us like a current cost, right? You have the current length, right? Plus the left side, the left subproblem, then the right subproblem. And also we min that with the running min that we've seen so far, right? So hopefully that makes sense. And again, I'm going to show you my solution, but I don't think it's actually the cleanest. So this is how I solved it. Oh, actually I'm showing you the editorial first. Oh, okay. Just didn't want to show you mine first. So the editorial did a for loop in a very long line of code, but basically for each midpoint that can happen inside this interval, right? So basically this is the left, right? And this is the right. And the mid, like these are the candidates for the mid, okay? And what happens is that they decided that they could basically take the cost of the left subproblem, right? This is the left mid, so this is this subproblem, right? And then they have the right subprom also when they do this right here, right? This is in salmon, and this is also in a salmon color, right? And you add the cost, you add the current interval, and the current interval of that cut is, well, to the right and to the left, right? So these are fixed for the particular problem. They could have probably saved this in a constant and moved that into a nice looking variable, but I guess they didn't do that. But yeah, this is the interval length, right? You can check out their base cases too. One of them is just if they memoized it, and honestly I feel like they missed an opportunity to do an at cache kind of thing above this function definition. But the nice thing about writing your own explicit cache is that it's a lot easier to debug. You can actually print out your cache and then see what things got filled or not. So there's advantages to writing your explicit cache when doing top-down as well. So yeah, hopefully that makes sense for the problem. I wrote it in a much more, well, verbose way. When I write things out, I tend to talk to myself quite a bit. I do an at cache, and you'll see that I basically have the remaining part of the left part of the stick and the remaining part of the right part of the stick. This is a different recurrence relation. I actually have the left subprom and the right subprom put in this way. I would say don't get bogged too much about the details about the specific indices. One thing that's interesting to note is that stick left and stick right, I believe, are completely computable based off of left and right. So even though you see 4 different parameters, the third dimension, stick left, and the fourth dimension actually collapse, meaning that there's not much dimension to them at all. The stick left and stick right will always be computable, I believe, from the left and the right in this solution when I wrote it. So it's still O of n squared time complexity because of that, even if you have more parameters. This is something to note, however, when you start doing dynamic programming problems where even if you have the correct time complexity, sometimes the space complexity required for that problem might actually lead you to a memory exceeded kind of scenario. In which case you have to start writing your solutions such that you're only going to cache on a few different dimensions rather than more dimensions. So just keep a note of that if you're doing tabular, but we're not going to really talk about that today. So here's split array largest sum. I actually don't want to talk about this problem too much in depth, but I am going to tell you that, hey, when you read this problem, it should feel immediately familiar to a structure you've seen before. So basically you're given an integer array and an integer k, and you have to split up nums, right, into non-empty subarrays, right? So these are subarrays, so they're contiguous, and we know patterns about contiguous partitions, right? You just have to have k number of these partitions. And you want to return the minimized largest sum of the split. So basically this is a little bit like bookshelves but it's a little bit different because you need k bookshelves, and they have to be non-empty, but in the bookshelves problem it was already non-empty. So there are multiple different types of solutions to this, and even if you find a recurrence relation that doesn't work, I would still say that's good to jot down, because when you're starting to practice these problems, you're going to start seeing patterns and relationships within these different recurrence relations and be able to pick and choose which ones might work better for a problem. The curveball is that this one can be solved with binary search. Remember that binary search lecture? I talked about how great binary search is because you can actually just bypass going through dynamic programming solutions and just write a binary search solution, right? We didn't get to that point where we did a second presentation on binary search, but it's probably one of my favorite topics when dealing with problems of optimization. It tends to be like a lot faster than some of the dynamic programming solutions. And binary search also uses very little memory as well. So I've never done this problem using DP, but you can. There are solutions posted on LeetCode. So I would encourage you to try it with DP, and then one day maybe you'll decide you want to try binary search. All right, so regular expression matching, I don't have anything more to say on that. I feel like this is really good practice if you've never done this before. I'll just show you briefly this problem in case you watch this video but don't open the problem. Whoops, what's that on the right side? So given an input string S and a pattern P, implement regular expression matching, right? So off the bat, this list should look very familiar to another problem that we did. It was number 44. That was the wildcard matching. So I encourage you to figure out what pattern that you want to use and give this problem a shot. I think with some effort and some tweaking with the base cases, you should be able to get this one in the bag. All right, so let's get to longest increasing subsequence. Refresh yourself on which recurrence relation this was. So given an integer array nums, return the length of the longest strictly increasing subsequence. All right, so pause this video if you need time, but otherwise I'm just going to show you. We were talking about this before. This is when the current problem at index I depends on the entire range of increasing size, and it tends to increase contiguously, right? So basically, I'm going to choose this recurrence relation where we move I forward, and then the longest increasing subsequence at I depends on the longest increasing subsequence found previously over one of the indexes from 0 to I minus 1. This is one of the most common, most important recurrence relations that you're going to see in various problems. We often don't write this recursively, but you can. There's a website called Visual Algo that you can look at if you want to look at the recursion tree for this problem. And for this specific problem, for a of I, this is the value at I. How can it extend the longest subsequence seen at j, which occurs before I, right? And it also has the caveat where the value a of j had to have been smaller than a of I. Okay, so we'll see it all at once. So what data defines a state? Hopefully you should see that the current index is I, right? Because each problem input, right, each state of that recursion tree only needs that one little index. Okay, that's all you need. So what does each subprom return? Well, you build the longest subsequence ending at index I from the longest subsequences seen at index 0 all the way to I minus 1, right? So imagine if you knew if your current value is 7, but you knew the longest increasing subsequence that happened at this value 6, right, was something like 4, right? Well, one candidate for the current longest sequence is now, well, 4 plus 1, right? Because 7 can tack onto this 4 right here, right? So if you find something like 0, right, if the value was actually 0, well, there was nothing greater than that. So 1 plus 1 is also a candidate, right? So you're looking at the answers, right? These are all the answers. Was this 1 right here? Was this 4 right here, right? It happened at this particular index, right? At this particular index, I don't know, let's call that P, the longest increasing subsequence is 4, and you're able to use that because 7 is greater than 6, okay? And you do that comparison with every single thing here, and there's smart ways, actually, to use this same recurrence relation and get an O of n log n solution. But we're not going to worry too much about that. I just want to focus on actually getting that recurrence relation. So the base case is you start at 1 for each number, right? Because each number is itself can be its own sequence, right? All right. So how do we combine these subproms? Well, hopefully you saw from the description here that you could use basically a nested loop. And here's what that looks like. Again, this is not particularly fast, but I just wanted to illustrate the recurrence relation. Okay, you're going to see this a lot in different problems, and you can write a recursive version for this function. And this is how you relate to those subproms, right? You keep this cache where you kept everything that was saved, and you access it on index j, right? So this code is O of n squared, right? But that's all I'm going to show you for this problem. So let's talk about, okay, so I'm actually not going to talk too much about this one. I'm going to gloss over it a lot. So basically the gist of this problem is basically you have a number of restricted paths, but first what you need to do is figure out the shortest path to the destination from every single node, okay? So I'm just going to focus on the part where, hey, when you deal with a graph, and if you're starting to formulate this as a dynamic programming problem, your head should immediately jump to Dijkstra. Also, what's important about this graph is it's undirected, right? And it's weighted, right? So you can most likely use Dijkstra here. One thing you have to guarantee, of course, is that the edge weights have to be non-negative. So you can deal with weights that are 0, but if it was negative, you wouldn't be able to use Dijkstra, okay? But here you can, under these constraints. It seems like Dijkstra would work for this type of problem. So basically, that's kind of the main point I wanted to get across. There is a portion where you might want to do a cached depth first search in order to calculate the number of restricted paths, but I didn't actually really want to talk too much about that. I just hope that you recognized that this was a Dijkstra problem, where you saw the shortest path from P to Q, you saw that to get from the shortest path from P to Q, you need to go through the shortest path, the shortest ways to get to the neighbors. And from the neighbors, you'll reach eventually recursively all the way to Q, right? Of course, when you write Dijkstra, again, you use a while loop. It often looks like a breadth first search implementation. So that's all I want to say. Apparently I messed up this slide. Sorry about that. So what defines a state in a Dijkstra problem? It is actually each node in the queue is a state. And when we write this in Python, as we often do, we keep each state, the cost is the first element of the tuple, just because it's a quirk of how the heap queue library works, and the current node we're actually at. So it is a cost associated with the node. Most of the time when you use Dijkstra for most implementations that you're going to see online, it's actually E times log E times complexity. So data defines a state. Sorry, that was really long-winded. It is really the cost associated with arriving at the particular node sub I, right? And what does each problem return? Well, it's not really correct to call it returning since our subproblems aren't done by DFS. But regardless, each subproblem, right, also has the optimal substructure property, right? If I'm arriving at some node n, right, the min cost has to come from the min cost it took to arrive at the neighbors of n. This would be something like P or Q, right? So what are the base cases? So this isn't recursion, but we do stop expanding under these two conditions. Those conditions, which you cannot see on the screen, happen to be when we have seen, right, this neighbor before, right? So basically we've cached a less costly way to arrive at this neighbor before. The other case is when the queue runs out of nodes, right? There's no other further neighbors to explore for a particular node, right? So those are our base cases. And the cost that we start off with is 0. And it just gets accumulated as we keep going on. So the subproms in Dijkstra, I think I'm belaboring it actually a bit too hard. So I'm going to stop talking about this problem. All right. One thing is possible to actually only use Dijkstra in this problem and omit the DFS that I write that is cached later. I haven't figured out how that works, so I haven't presented it or written it that way yet. But there are wonderful solutions that you can find online that talk about that. Okay, I messed up this slide too, somehow. But this is the longest common subsequence problem. And you're given two strings, text 1 and text 2, and you want to return the longest common subsequence. So a subsequence of a new string is generated from the original string with some characters being omitted. Okay, you cannot change the relative order of the remaining characters. So basically they're saying A, C, E, right? So you pick this A, you pick this C, and you pick this E, right? That's a subsequence, right? If you picked A, B, C, that is also a valid subsequence. You want to find the longest one. For this example, it is actually A, C, E. For this one, they're the same string, so the longest common subsequence is the string itself. And basically, you can look at this and you're like, huh, an O of n squared time complexity solution might work. Okay, so what is the pattern that's going to be used here? So pause the video and think about it. And, all right, time's up. So this is basically you compare prefixes of different sequences. This problem should look quite a bit like edit distance, if that's the case. Hopefully this is starting to solidify things for you. I'm going to pick this recurrence relation where we depend on the answers of the suffixes, right? So basically, I guess, are we going to do it on this one slide? It seems a little difficult to fit in. So what defines a state here? Well, you should see that ij, right? So you have an index for the first word and the second one for the second word. I might have copied and pasted this, sorry. So what does each subprom return? Okay, this text is absolutely wrong. The subprom actually returns the longest it returns the length of the longest common subsequence. For this problem, you don't return the common subsequence, you just return the length. So it is actually, scratch this out, it's the length of the common subsequence of longest common subsequence of the suffixes, right? And the suffixes that start at I and the suffix that starts at J. Yeah, I and J right here. So what are the base cases? Well, if you got to the longest common subsequence as being empty string, you should probably return 0, right? Because then there's no more common subsequence, right? So what I did in JavaScript was make an explicit cache of basically what it looks like of text 1, right? Text 1 is this dimension, and then text 2, right, is this dimension, right? So the columns is in text 2 and the rows is text 1. And this should look really familiar if, again, you read chapter 3 of Jeff Erickson's wonderful algorithms book. So yeah, this is the base case. So when we get to the end, and in JavaScript, you're basically going to have a nullish value. It's going to be undefined. I tend to do this double equals with null when it's either null or undefined. It's the only time I use double equals in JavaScript. So that's the base case. And then of course you have your cache base case, which you should expect. And now this should look a lot like edit distance, right? But it's a little bit inverted from edit distance because when the characters match, that's when we add something, right? When the characters don't match, we don't add anything. Notice that there's no +1 here, right? It's not there at all. Because when the longest common subsequence, we find the things that we don't have to change. So we don't have to change anything when car1, right, equals car2. And then we basically increment both indices, right? Because now that index is taken already, right? We're able to say that, hey, this current APPLE is APPLY. If we're at this P and this P, we're saying, hey, these are the same. We're just going to put this as part of our subsequence, the longest length, based off of these two starting positions at their respective strings. Otherwise, right, if they're not equal, well, we have the ability to advance, right, the first string, right, get the suffix, get the next suffix of the first string, and keep the second string the same, right? Or we can advance the second string, right? This would be this string right here, and keep the first index for the first string the same. So hopefully this looks like, you know, is not too hard to visualize, but I really encourage you, if you had problems with this, just try this problem again after you've had a good night's sleep. That'll really help you solidify. When you think about things that are important to you when you sleep, your brain is actually going to help you solidify and create those connections in your mind. I would say that the best pattern that you can use to get better at problem solving is actually sleep. So hopefully you prioritize your health in doing that. How many problems are we doing here? This is quite a lot. So anyway, whoops. Anyway, this is coin change 2. And hopefully you've done problems where you've dealt with combinations before, because this is going to look a lot like those patterns that we use for combinations. The gist of this problem is basically you have this amount and you want to create it exactly. And how many combinations, right, can you make out of these coins that creates this amount? So for example, for 5, you could make it using, oh wait, it's right here, right, using 1 5, or you can use it using, you can make it using 2 2s and 1 1, or 1 2 and 3 1s, or just 5 1s. Notice that this is a combination problem, right? So 2 plus 1 plus 2, right? That's not valid. Or that you can't count that in addition to this 2 plus 2 plus 1, right? This would be double counting in this case. So this is different than the count stairs problem, the climbing stairs problem, right? The climbing stairs problem is a permutation problem, right? So its structure looks a little bit differently. But anyway, this is the coin change problem, right? And we want to figure out how we can, how many ways, essentially. And you have an infinite number of each coin. Okay, so this problem is, I'm about to tell you a bunch of stuff, okay? Look at these constraints. There's going to be at least, at most 300 coins, and each coin's value is bounded by 5,000, okay? All the coins are also unique, as they should be, since you have an infinite amount of each type of coin. Yeah, and the amount that you'll need to be making is 5,000. So these are relatively, these constraints are the way they are for a specific reason. It's because the type of solution that they're going for is a DP solution, where it's not linear, right? So what kind of problem, what kind of pattern can we use for this? It's knapsack-like, actually. And we try to find out how we can make every single amount using only a suffix amount of the coins. This is the main realization that you can use, or a main line of reasoning that you can use to create that recurrence relation. So it's a combination problem, so the order of coins doesn't matter, and we have to be intentional about the depth first search, okay? Unfortunately, I guess I messed up on that. Anyway, it looks like a wall of text, so anyway, what data defines a state? Okay, hopefully it shouldn't be too hard to see. The data that defines a state is not only, well, actually, this might be a little bit more complicated than the other examples because I apparently did not write it out. There's going to be two things for the recurrence relation that I'm going after. One is the current coin index, right? Another aspect of this problem is I'm going to talk about the remaining amount. And so it's the amount remaining or the coin index. The order doesn't matter of how you define your state. So what does each subproblem return? Okay, so it's actually the same thing as the main problem. This is how you have overlapping subproblems, right? And a way to combine them. So the number of ways to create the amount using only that suffix of the remaining coins. You also don't want to revisit a denomination of coin ever, right? If your DFS sequenced in such a way that you could revisit a coin denomination, then you might run into a situation where 2 plus 1 plus 2 equals 5, right? We don't want to do that. You basically want to choose all of your 2's. You basically, if you're going to choose something, they're going to be all chosen, right? 2 plus 2 plus 2 plus something, and only then can you move on to different coin denominations, right? So we have to be smart about the depth first search, very intentional about it. Okay. And what are the base cases, right? What happens if you keep going on to the recursion? Well, coin index could be exhausted, right? You're at the end of the array of the coins, or the remaining amount might be negative, right? It might be less than 0, or it might actually equal 0, right? Two different things happen depending on these cases, right? If you have 0, then you're successful, right? Then the way that you got there was one valid path, so you could return 1 in that case. But if it was less than 0, you return 0, right? There's 0 ways. It wasn't valid, essentially. All right, so how are we going to combine these subproblems? And this basically, we're going to use pick or no pick, right, as our main pattern. So this is one way to write it. I think this is the slower way. Recursively, it took like 8.5 seconds, okay? So you see my base cases up here. I start off with noting how many combinations I found, given the current amount remaining, right? And the current index at this coin index. So notice that I did this problem in a way where, like, for this I, right, for this amount, I have a particular I, right? Sorry, that did not show up very well. I is basically my start. And basically it's the start for the coin index. And the coin index is right here, right? And each time I can decide to start this new subproblem of this coin index, right? And without moving the coin index, right? I'm changing the amount, decrementing the amount, but I'm choosing to say, hey, I'm gonna basically keep the coin index the same, essentially. If I wanted to change the coin index, right? I wanted to decide, hey, I want to move on to a different coin index. That's going to happen after I increment, right? After I do this for loop, right? And I increment the coin index right here, right? Then I'll have incremented it here, and I'll have aggregated the amount of ways in this current subproblem, right? And then I leave it up to the subproblem to tell me what happens if I decrement the amount, right? And go further. I would actually not recommend using this type of recurrence relation for this problem. It actually turns out to be quite slower than by a magnitude when you use the pick or no pick pattern. I think this one is much more intuitive to realize. So here it is, another base case when you do it like this. The coin index is equal to, is exhausted. You return 0, right? Because you can't use coins anymore. I start off the combinations at 0, and then here's the subproblem that you saw beforehand, right? This looks very familiar. This is basically you reduce the amount, but you stay at your current coin, right? So you're picking to use that coin to decrement the amount, okay? And there's the path where you don't pick that coin. And you just increment the index without decrementing the remaining value, okay? So this k, the amount, right? That's basically why this time complexity is the way it is. So the amount of coins, right, is basically the variation for the coin, and the amount is basically the amounts that are possible all the way to 0 from k, right? I think this one's actually a lot more intuitive, and this one is actually faster. With that, I believe this is my last problem. So let's see if you can figure out the recurrence relation to this problem. So what is this problem? So you're given a 2 0-indexed integer arrays. Okay, so you have nums as an array and multipliers as an array. And you're also given that nums array is always going to be greater than or equal to than m. Okay, so you begin with a score of 0 and you want to perform exactly m operations. Okay, basically you're going to look to exhaust the multipliers. And basically you can take the first multiplier, right? You have to go through these one at a time from left to right, okay? And you decide whether to multiply the right side by this 3 or multiply the left side by this 3. Okay? And you keep summing that to your score. So let's say the best way was actually, let's say you pick this path, right? Then your current score was 9, right? Then you have this 2 and you decide whether to multiply 2 on the left or 2 on the right. So that's basically it. Yeah, that's that problem. So let's jump into which pattern does this look like. It's the one where we shrink on interval bounds, right? This problem is pretty easy to visualize. All right, but what defines a state? Well, this problem looks a little bit different than this pattern, right? In addition to maybe having to keep state on the bounds of nums, you also have to keep state on like where you are in multipliers, right? So it's actually going to be 3D, right? You have the I, comma j, but you also have multipliers index, okay? So that's what defines a state. And if you use a tabular solution, the downside is based off of these constraints, you might run out of memory when you initialize all those cells. So you need a way in order to collapse the memory, because if you look at it, this is 300 by 10 to the 5th, right? And then by 10 to the 3rd, right? This is going to far exceed the amount of memory that you're allowed, right? So the way that if you're doing tabular, you have to find a smart way to break down the dimension. This is why I don't recommend you trying to do tabular approaches first. It is a lot more performant in a lot of ways. You can find ways to save memory. But the naive solutions, they're trickier to get right when you do a tabular approach. I really do recommend you start with just the recursive solutions as much as possible, as long as it's easy to do, right? With those explicit grid problems, like it's much easier to write them in a tabular approach. But get comfortable with the recursive stuff first, okay? There is a trick to it. You can shave off to create a 2D cache instead, but it's still essentially the same amount of states to compute. Remember, when you use a tabular approach, you're not going to save on time complexity. You're going to save on space complexity. So if I doesn't move and multipliers index moves, this means that the right index was chosen. And if I moves, right, and I, in this case, is the left index of nums, right? If I moves and multipliers index moves, that means the left end was chosen, okay? So basically, those are your two states, left IDX and multipliers IDX. And based off of the amount, based upon how deep you are in multipliers, and you can look at left index, you can actually calculate the right index. right? That's calculable. Don't worry too much about that. Just stick with the recursive stuff. So what does each subproblem return? Well, because this is a maximization problem, it should return the maximum score of a particular I and j interval bound with a suffix of multipliers, right? What are our base cases? Well, you could exhaust multipliers, right? Hopefully this is starting to feel very familiar to you. I just tend to think about how deep can the recursion get? What does it mean to be all the way at the end? So if I'm at the end of multipliers, well, there's nothing else you can multiply. So I think in that case, you want to just return 1 since you're going to be multiplying stuff. Or actually, no, I think you're probably adding, right? So yeah, you're going to return 0 if you're out of multipliers, if you exhausted multipliers. In this case, what's very interesting about this problem, or very nice about this problem, is that you never have to worry about like nums exhausting before multipliers exhausts, so you don't have to write a base case for that. Okay? So I think this is all you need. And for this problem, I guess I did this problem a long time ago, which is why you're seeing them in JavaScript and not Python, as I've done for a lot of these presentations. So these are my 3 states, right? I use DFS, I create my own cache. If I'm at the end, I just return 0 because I'm going to be adding the subproblems together, right? So this is basically if I move the start, right? So if let's say I have I and j, right? The subproblem is when I move I, right? And I keep j where it is. The other subproblem that's right here is when I decrement j but keep I, right? So I just want the maximum of these 2 options, and I'm just going to cache that and then return the score for the current subproblem. And so I'm choosing the start, right? The start value at the left end of the array has to multiply against the current multiplier that I'm at, right? And you'll see that I advance the multiplier no matter which path I go to. And this should look a lot like depth first search, right? It's just DFS. So hopefully this was a relatively straightforward problem. Yeah, it's listed as hard, but it feels pretty intuitive to kind of get this type of code out. Oh, I will say, maybe don't copy how I did this. You're actually going to be, well, I don't know. When you use a cache and you like build keys this way, you kind of don't have to care about collapsing dimensions as much, which is why I do it. It's a pretty lazy way to do it, and I'm a fan of not thinking too hard, unless you need to. So those are the problems. There's many other types of recurrence relations we did not go over, but I think that this should give you a really good footing on a lot of these. And so these are some topics that you can start exploring, and if you want to present on these, great. I'd be happy to watch your video or give you feedback as you create these for yourself and for others, right? Creating publicly visible work for others to see. So writing tabulation from recursion, I might actually do this at some point. I'm not sure if it's going to be part of this season. Another thing is to be talking about space efficiency with respect to tabulation. I think it's worthwhile to separate this as its own kind of presentation, as there are quite a few things you can talk about. You can talk about state dimension reduction, which is something that you might see from a problem like this, right? You could technically just have start and multiplier index and just calculate what the end would be based off of these 2, right? It doesn't save you time, but it could save you like a little bit of cache space if you're creating all the cache space explicitly, as you do when you do a tabular approach. There's also topics like keeping only needed entries for the recurrence relation. So for example, that robot minimum path sum problem, you can just keep a current row essentially, and just not worry about other rows. But since you're overwriting the cache since you're actually mutating the grid directly, it's of one memory anyway. But there are ways in which, like you'll see in the Fibonacci numbers, right? Fibonacci of n, right? There's a way to collapse that entire recursive tree, right? If you're looking at 5, 4, 3, 2, and 1, and this would be what, -2, so 3, 2, 1. Anyway, I'm not going to draw out the entire recursive tree. There's a way into having just O of 1 memory, right, while doing essentially this entire problem in a while loop, right? So that is also an advantage of writing tabulation. There's times when recursion beats top-down, beats the bottom-up tabulation, is when the recursion tree happens to be sparse, but tabulation is dense, right? Tabulation, like you're gonna go through like all these different states when the time complexity is O of n times n, right? Whereas the final solution, if where you want to is calculate state for this state, it might actually only care about like these particular states, in which case you've just used up a bunch of like time to calculate things that are not actually part of the recursion tree. That can be the case, and that's when top-down actually beats in raw time in milliseconds over tabulation. All right, so there's other recurrence relation patterns we didn't see. There's things like binary lifting, there's other types of dynamic programming on trees, there's state machines, and of course we didn't talk about greedy problems, but there are greedy approaches to some of the problems that we saw today, I believe. And if not, I also have the presentations in org mode that I've commented out, and when building this presentation, you didn't see those. But if you look at the source code, and I'll eventually upload all the source code for the slides, you'll be able to see some of those problems that I omitted, just because I just didn't feel comfortable presenting on them today, or didn't have time. Of course, there's binary search for optimization instead of dynamic programming. It works some of the time for some problems, but this is a very cool pattern to use. And there's also advanced dynamic programming. I feel like some of these topics are for a graduate level course. I'm not sure what LeetCode problems I'll have to practice on these. I haven't looked too much on these sections, but these would be wonderful if you wanted to present on them for algorithms, for algorithm patterns in practice. Thanks so much. You can send at me for whatever reason, and maybe I'll see you next season, if there is one. All right, have a nice day, and bye.